What if the ground beneath your feet, right at the edge of the ocean, wasn't just sand? What if it was a graveyard?
Now that sounds dramatic, I know. And to be fair, not every beach is the same.
But for so many of them, the story is one of the most epic tales our planet has to tell. Every single grain of sand on a classic beach is like a ghost.
The last tiny remnant of a mountain that was born in fire and died in slow motion over millions of years. It's a tale of violence and incredible patience, of cataclysmic force and impossibly slow change. It's an epic that unfolds over a timescale we can barely comprehend.
And its final chapter is written right here, in the soft grit between your toes. To really understand the beach, we have to go back in time.
Way back.
Back to the violent birth of the very mountains that would one day become these shores. Before a mountain can die, it has to be born.
And mountains aren't just giant piles of rock. They're the colossal wrinkles on the face of our planet, built by the slow, unstoppable crush of continents.
Deep beneath us, the Earth's crust isn't one solid shell. It's a mosaic of enormous tectonic plates, which float on the upper mantle. And while it isn't a literal sea of molten rock,
this layer, the asthenosphere, is so hot and under so much pressure that it can flow like cosmic caramel,
carrying the rigid plates on top with it. When two continental plates collide, the forces are genuinely unimaginable.
Rock, which we think of as the very symbol of solid, behaves like a fluid.
It buckles, it folds, and it thrusts upwards.
Mile after mile of crust gets squeezed, rising higher and higher over millions of years. This process is called orogeny, and it's how the great mountain ranges of our world are born.
The Himalayas, the Alps, the Andes.
While these collisions are always accompanied by earthquakes that shake the world, they don't always involve volcanoes.
Many of the greatest ranges are formed by pure tectonic muscle.
For a while, these new mountains are jagged, sharp, and seem invincible.
They are the anti-erosion, building the world up faster than it can be torn down. But even as a mountain reaches its peak, its death warrant has already been signed. The moment it's exposed to the air, the forces that will destroy it begin their silent, relentless work. The clock is ticking. So how does a fortress of solid rock begin to die?
Not with a bang, but with a whisper.
It starts with a single drop of water.
The process of breaking down rock is called weathering, and it's a two-pronged attack, physical and chemical.
Together, they're a conspiracy of destruction, turning stone into dust.
First, the brute force, physical weathering. This is just mechanically shattering the rock. One of its most powerful tools is deceptively simple: water and cold. Rainwater seeps into a tiny crack on a high cliff face.
As night falls, the water freezes.
When water becomes ice, it expands by about 9%, acting like a tiny, powerful wedge being driven into the rock.
This is frost wedging.
Dawn comes, the ice thaws, and water seeps a little deeper. Night falls, it freezes, the wedge drives deeper.
Repeat that millions of times, and it acts like a slow-motion jackhammer, prying loose huge blocks of rock that crash into the valley below.
Heat is an accomplice too.
On a sun-drenched rock face, the surface bakes and expands, while the inside stays cool.
At night, it rapidly cools and contracts.
This daily cycle creates stress. Causing the outer layers to peel away like an onion, a process called exfoliation. But as powerful as that is, the silent, invisible attack of chemical weathering is what truly dissolves the mountain's soul. If physical weathering is the hammer, chemical weathering is the acid.
The main weapon?
Water again, but this time as a chemical solvent.
As raindrops fall, they dissolve CO2 from the air,
forming a weak carbonic acid, the same stuff that gives soda its tang. On a rock like limestone, this acid works slowly to dissolve it, jinghibaspooned,
carving out vast cave systems over eons. For a hard rock like granite, a composite of minerals like quartz, feldspar, and mica,
the process is more complex.
The acid rain attacks the weaker minerals first.
The feldspar reacts with the water in a process called hydrolysis, basically breaking its chemical bonds and turning it into soft clay. The granite structure is now shot.
The hard feldspar crystals have turned to mush.
leaving the tough, resistant quartz grains just hanging there, unsupported.
It's death by 1,000 cuts, turning a solid mountain into a crumbling shell of its former self. The mountain is now broken.
What was once solid rock is now a jumble of boulders, gravel, and chemically rotten debris. But this rubble doesn't just sit there.
This is where erosion kicks in.
If weathering is breaking the rock, erosion is carrying the pieces away.
This is the mountain beginning to bleed its very substance into the arteries of the planet.
The most immediate force is gravity.
A boulder pried loose by ice falls.
This constant rain of debris forms vast, unstable slopes of scree.
A small tremor or a heavy rain can trigger a massive landslide,
sending a river of rock thundering into the valley. But the true architect of the mountain's disassembly is water.
A single raindrop hits the loose soil, dislodging a few particles.
That water gathers into streams, creating a network that is the planet's circulatory system. This flowing water has energy. It picks up the loose material, the clay from the rotted feldspar, the grains of quartz, the small pebbles,
and carries it along. This is the mountain, now liquefied and set in motion. In the high mountains, these streams are steep and ferocious, rolling boulders the size of cars, scouring the landscape. The particles of rock, now officially called sediment, have been conscripted into the river system. The mountain is no longer a static landmark. It's a flow of matter destined for the sea. The river is now the master of the sediment's fate.
What began as a trickle is now a powerful force,
acting as a planetary-scale grinder and transportation system. The journey of a single grain of sand is an odyssey of violence and transformation.
An angular, fist-sized chunk of granite tumbles into the headwaters. It gets bounced, smashed, and dragged along the riverbed, colliding with thousands of other rocks.
This is attrition.
It's a relentless rock tumbler, and with every impact, our granite chunk gets chipped and smaller. Boulders become cobbles, cobbles become gravel, and gravel becomes sand.
At the same time, the particles are being rounded.
All those collisions knock off the sharp edges.
An angular grain of sand is a young grain. It hasn't traveled far.
A smooth, rounded grain is a well-traveled veteran. The river is also a brilliant sorting machine.
In the steep, fast-flowing mountain sections, the water has enough energy to carry everything. But as the river hits the flatter plains, it slows down and loses energy. It can no longer carry its heaviest load.
The biggest boulders get dropped first. Then the cobbles, then the gravel.
You see these forming gravel bars in the upper reaches of rivers. By the time the river gets near the ocean, only the lightest materials, sand, silt, and clay, are left.
The river has sorted its cargo by weight.
Which is why the mouths of major rivers aren't typically littered with boulders.
The heavy lifting was done long ago, far inland.
This journey isn't continuous.
A grain of sand might travel a few miles in a flood.
Then sit on a sandbar for 100 years, waiting for the next big storm to move it again. But eventually, after a long and brutal journey, it approaches its final destination.
The great equalizer, the ocean. This is the final transition.
As the river's freshwater flows into the salty sea, its speed plummets to nearly zero.
Its energy is gone.
And with that, the river is forced to do one last thing. Drop everything it's still carrying.
This massive deposition of sand, silt, and mud creates a delta.
The Mississippi Delta, the Nile, the Amazon. These are some of the most fertile places on Earth, built entirely from the weathered ruins of distant mountains.
The sorting continues here.
The heaviest particles, the sand, are dropped first, forming sandbars.
The even finer silts and clays are carried a bit further out, before settling in calmer, deeper water. The river's job is done.
It has delivered billions of tons of rock, ground down to fine particles.
To the edge of the continent. But for the sand, the story isn't over.
It has arrived at the coast, but it has not yet arrived at the beach.
Now, it has to face a new and even more relentless force: the ocean itself.
The sand is now in a war zone.
The coast is a place of ceaseless energy from waves, tides, and currents. This is the final refining process. The coastal crucible that turns the river's raw deposits into the clean sand of a beach. The waves are expert sorters. When a wave crashes and retreats, the turbulent water picks up all the sediment.
But the heavier sand grains settle out quickly,
while the much lighter silt and clay particles stay suspended and get washed out to the sea.
This winnowing process, repeated with every single wave, is incredibly efficient at cleaning the sand.
which is why beaches are sandy and not muddy.
The ocean has meticulously washed its material, keeping the sand.
And discarding the rest into the deep.
This is also the final test of durability. And the undisputed champion of survival is quartz.
Made of silicon dioxide, quartz is chemically stable and physically very hard.
While minerals like feldspar were turning to clay back in the mountains,
The quartz grains just got a bit smaller and rounder.
most light-colored beach sand is composed mainly of quartz, a testament to its incredible resilience. While most quartz comes from igneous rocks like granite, it can also be weathered out of other rocks like sandstone, beginning its journey all over again. Finally, the waves and currents move the sand. A process called longshore drift acts like a river of sand flowing within the ocean.
Constantly moving sand parallel to the shore.
This is how sand from a river mouth gets distributed to form beaches that can stretch for hundreds of miles.
A beach isn't a static thing. It's a dynamic, moving pile of sediment.
A temporary graveyard where the ghosts of the mountain pause for a few thousand years before continuing their journey.
So, we've followed the epic journey of quartz from a mountain's heart.
This story explains most of the world's classic, tan-colored beaches.
But to think this is the only story is to miss the staggering diversity of the world's coasts.
Let's go to the tropics, to the brilliant white sand beaches.
Look at this sand under a microscope, and you won't find quartz.
You'll find the pulverized remains of living things.
This is biogenic sand.
It's made from the ground-up skeletons of corals, shells, and microscopic organisms. But there's another, stranger contributor, the parrotfish. These fish use their powerful beaks to scrape algae off coral, ingesting a lot of the coral's rock-hard skeleton in the process.
They grind it up and excrete it as fine, white sand.
Depending on the species, a single parrotfish can produce hundreds,
or in some cases, even thousands of pounds of sand every single year.
So yes, when you're relaxing on that pristine beach, you may be lying on millions of years of accumulated fish poop.
These are graveyards of ancient reefs. Or head to a volcanic place like Hawaii or Iceland, and you'll find beaches of pure black sand.
When molten lava hits the cold ocean,
It shatters explosively into tiny fragments of black volcanic glass.
these are young, fiery beaches, born from the Earth's inner fire.
The variations are endless. There are green sand beaches in Hawaii made of a dense volcanic mineral called olivine.
Bermuda's famous pink sands get their color from the crushed red shells of an organism called foraminifera.
The color and composition of sand is a fingerprint of its origin. Every beach is a unique library, telling a geological and biological story. And so we return to the beach, but with new eyes.
A handful of sand is no longer just sand.
It's a time capsule.
In your hand, you hold the ghost of a mountain.
This little grain of quartz might have been born in magma 300 million years ago. It was lifted skyward, sat near a peak through ice ages. And witnessed the dinosaurs come and go.
Then one day, a trickle of acidic water finally dissolved the feldspar, holding it in place.
And it was freed.
It tumbled into a stream and began its great journey. It was smashed, ground, buried for 10,000 years.
Exhumed by a flood.
And finally reached the sea, where waves washed it, sorted it, and carried it here.
And it's not alone.
Billions upon billions of its brethren lie with it,
each with a similar, yet unique, story. Together, they form this transient, ever-changing landscape we call a beach. The sand between your toes is very often the last remnant of ancient mountains,
pulverized over eons. It's the final product of a slow-motion planetary grinder. It's a system of creation and destruction that defies our human timescale.
So every beach is a graveyard, yes.
But it's also a nursery.
That very same sand, if buried offshore and compressed by millions of years of new sediment, can be transformed back into rock, sandstone.
And that sandstone, through the endless churning of our planet,
could one day be lifted up to form the peak of a new mountain.
the entire cycle would begin again.
The next time you walk along the shore, take a moment.
Feel the ground beneath you.
You're not just walking on sand.
You're walking on the dust of worlds.
You're walking on the crystallized memory of time itself.
You are walking through a graveyard of mountains. A testament to the fact that on this planet, nothing is permanent, and everything, eventually, is returned to the sea.
If this journey through deep time sparked your curiosity, subscribe for more stories about the hidden workings of our incredible planet.
And let us know in the comments what geological wonders you'd like us to explore next.
Thanks for watching.